Okay, so we're here. We are here and on your handout. And let me activate my pen here. Okay, so queuing system. So we already saw there's two kinds of queuing systems. And we're going to waiting line system is with what it is in the queuing system, and it has two parts in the system. And this is a picture I lifted out of a Wall Street Journal article. I should really say somewhere, but I'm telling you now, this is from a Wall Street Journal article, and they talked about how the stores are trying to manage their waiting line system to make it more efficient, so the customers will actually come to the store instead of continuing to go online shopping. Okay, so this is an example of a queuing system, and there's two places here. You have here the lucky person here is receiving a service. That is, the person is purchasing something, paying for something. So that's your service area here, service area, and here's our customer. That's our customer, and here is our server. Here is our server. So a service area that must have some kind of server. That server could be a person, or maybe it could be a machine, like an ATM machine. That's also considered a server. And the waiting line is over here. Now these people are still waiting. They're still waiting. So this is a queue. Here is where people wait. And here we could see, okay, how many customers are in the waiting line? Well, let's see, we got 1, 2, 3, 4, 5, 6, 7. It would say 7 customers are waiting in line, and you have here 1 customer receiving a service. Okay. Now, when you are managing in a retail store or wherever customers have to wait in line, you gotta kind of strike some balance between the good service and saving money. So if you have one server and there's like a lot of customers waiting in line, that's not really a good service. Then because you are wasting people's time, and when you make customers wait for a long time, then that discourages them. It makes them unhappy, and some of them might just leave without paying for their purchase. Some of them might tell their friends, "Well, when I was at this department store, I had to wait." Like 20 minutes to pay for my stuff, so I'm never going to go back there, and you shouldn't go there either. And so you get this bad reputation. Everybody is kind of feel like each person tells their 2 friends, and those 2 friends tell their 2 friends, and so forth, and exponentially increasing bad reputation. Now, on the other hand, if you try to really provide good service by providing lots of servers, lots of cashiers, checking out the customers' purchases. What is it? Now the positive thing is that customers will be happy because they're not wasting time. They don't have to wait very much. But what is the downside of providing a lot of servers? Right, there's a cost. You got to pay these people. So you have more employees serving your customers. You got to pay all these employees. So there is a high cost. So people try to make these kind of managers try to strike some balance between that the high cost and the good service versus the low cost and bad service. Like place like Disney World is like they're like masters at managing the lines, and they have a bunch of people. I think they call them Imagineers. And imagination engineer, so Imagineers who work on this kind of stuff like full time, how to manage the lines and how to make the customers think that they're not waiting that long, so maybe entertain the customers. So besides like trying to have a lot of the rides open, they think of they have things like what's called fast pass, where you could kind of make a reservation for some rides. So people that would reduce the waiting time in line. So queuing is, I think, it's a pretty interesting subject, and it actually originally came from telephone, like in the old days when people first, Alexander Bell, invented the telephone, and in the old days that the people had to call the switch operator to make any phone calls, and you have to wait for your phone call to get through. So there was like a queue of phone calls that needed to be connected, and that's where people started kind of studying the waiting systems. And now it's applicable in many situations, and wherever there's some kind of operation, like so it could be, so like the people who are, I mean the queue could consist of not just the people waiting in line, but also like cars going through the toll, going through the toll booth, or even the products that the company is making, or maybe even the clothes that a store is selling. So or money that that is being kept in the bank vault, and so very kind of closely related to like inventory systems. Okay, and here's a kind of structure of a queuing system. We talk about, there's different kinds of queuing systems. There's different ways to distinguish characteristics of the queuing systems. One characteristic is the arrival process. What is the arrival process? Do people make appointments, or do they just show up? For instance, if you go to, let's say, if you go to McDonald's, okay, if you go to McDonald's, do you have to make a reservation? No, you just show up? Is that kind of inconsiderate? No, they're not expecting you, and you just show up. What if they're not ready? What if they're really busy? We have, like a lot of lots of.
It's 24/7.
Oh, it's
Always ready.
Always ready. So it's their job. So it's their job to be almost ready. It's like that's what they like. Fast, efficient. You come in and you just call. You come in and then you take your stuff and out. Their starting point is the speed, not necessarily the gourmet food. But it's more like speed, fast, cheap, so you don't make appointments at McDonald's. So you might say the arrival process to McDonald's is random. So that's the random. Like for example, McDonald's. There are many systems where we have arrivals are random. There's always people are waiting in line. That's a very common thing people do. And even if you go to some sporting event or the Broadway show or a concert, during the intermission, and you gotta go. A lot of people go to the restroom, and you see long line of people waiting for the restroom. Now, do you usually see a lot of men waiting or a lot of women waiting? Sporting events or shows, places like that. Well, last time I went, it was women's line was really, it was just it was extended all the way across the lobby and back, and there was hardly any men waiting in line. And it's been shown, so there is actually this phrase called party parity, and there are some states where the laws have been passed. In some federal buildings, you gotta have at least twice as many stalls in the women's restroom as opposed to the men's restroom, because it's been shown by serious research that the women's take twice as long to take care of business. So it's not just time they spend checking their makeup and hair, not that. I mean, the real business they take they take twice as long, and so it seems to make sense that there should be more stalls for women. But on the other hand, I think there was a football stadium where they did this. They built a lot more stalls for women than men, but it turned out a lot fewer women went to watch football. So now it's men were waiting for a long time. So it's just those public restrooms. That's a serious issue, and they should really do some research before they design these things. Well, anyway, so that's why we need some queuing theory, like we're learning now. Anyway, right, random McDonald's. That's what we're talking about, and the deterministic. Okay, if you make appointments. Like doctors might see you every 15 minutes. Doctor's office might see you every 15 minutes. Then you have a deterministic kind of system. Deterministic means that it's kind of predetermined. You know when people are going to arrive. You know they're going to arrive like every 15 minutes or so. Okay, and there's a term that we need to learn. Arrivals that occur randomly and independently of other arrivals. So independently means that it doesn't matter when other customers arrived. So when the next customer will arrive is totally independent from when the other customers already arrived. So each customer acts independently from other customers. And we call it a Poisson process. If you have a very random arrival process, then we could model it as a Poisson process. That's a kind of term that we need to know about. Okay, and the service times, that is like how long it takes to serve a customer. How long it takes to serve a customer could be deterministic or random. Now, if you have like a robots that are processing these parts that go into some product, then you could say service times are probably deterministic. It takes the same amount of time for each part to process each part. But then if the server is a human, like at McDonald's, you have and the customers have different orders. Some customers want 5 value meals, and some customers want just 1 hamburger. So depending on the size of the order, how long it takes to serve a customer is going to vary. And also, some servers are faster than the others, and sometimes servers are tired and they don't, they're slower. So it's kind of variable how long it takes to serve a customer. So then, if you have random service kind of process, then we could say the service times are typically modeled by an exponential distribution. And these are the terms that we're going to see. You're going to see like in the problem statements. So you should know what they are. And another characteristic is how many servers, how many people are working, serving the customers. Are there 3 servers, 2 servers, 5 servers, or 1 server? Okay, and as we discussed before, if everyone in line is served by the same server, then we call it a single server system. So you have a line, you have a server. Here's our server here, 1 server, and then 1 line. Okay. Now, if you have one line that's served by several servers like this, and you could go to one of these. You go to one of these, like at a bank. Let's say a bank. Then we call it a multiple server system. So here the point is, the important thing to note is the system should have 1 line. A system should have 1 line. So this is one system, and here is another system. Here's another system. Okay, let's look at another picture here. Okay, so this is considered a multiple server, multiple server system. This is a one multiple server system. We have 1 line, and that's served by many cashiers, many servers. Now would you say this is a multiple server system as well? Is this a multiple server system? Looks like there's 3, more than 1. So is this like multiple server like over here? Okay. Now, but the trick is that each system should have 1 line. Each system should have 1 line. So you gotta look at here's a system. Here's a system. Here's another one. Here's another one. So there's actually, you could say there are several systems here, several queuing systems. So we have 3 systems. So here we would say 3, and then each line is served by 1 server, so it's actually a single server. So 3 single server systems. So there are 3 systems, and each is a single server system. So this picture was also lifted off the same article where I took the other picture from. And here it talks about how, in the article it talks about how it's more efficient to have 1 line, like this. This is more efficient. This is more efficient than when you have several lines. When you have several lines, bless you. Okay. So that's why the Whole Foods, when they came to Manhattan, when they opened their doors in Manhattan, they really analyzed, they studied hard to come up with the most efficient system, and that's why they have a multiple server system. And then so like when you first when you first go in, it's kind of intimidating. There's like so many people waiting in line, but then when you count, how many servers there are, like you will see like line moves really really fast. Other places like started copying that kind of system. And I think there's now more of these kind of systems than before because people are inspired by Whole Foods. Right. Okay. Okay. And so like this is like it talked about how if you have like somebody who has a lot of coupons or something, the line stoppers that could really slow down the entire process. In this kind of thing. If you have a line stopper here, and these people are they're basically they're screwed. But here you have lots of choices. You could have somebody taking a lot of time here, but then you have all these other servers who are still available. Okay. Okay. So now we're going to kind of go to a simulation part. So to get an idea of what are the things we're looking for. So the QA model has, just like other models, have inputs and outputs. The inputs are like how fast are the people arriving, like mean arrival rate, and we start using Greek letters for some reason. And the mean service rate, how fast is the service going? How fast are the customers coming, and how fast is the service going? And those are the inputs. And of course, we need to know how many servers there are. Of course, if you have more servers, then it's going to go faster. And what are the things we're interested in? What are the outputs? We want to know how long the customers are waiting in line. That's an important measure, the performance measure. And what is the length of the line? What is the length of the line? And how long are the customers spending in the entire system? So not just in line, but also considering the service time. How long is the time spent in the entire system for each customer? So those kind of measures are the outputs. How efficient is it? We want to make sure customers don't wait too long. So how long are they waiting? That kind of thing. So we're going to kind of get a more kind of feel for all those characteristics by looking at a simulation here. So now we're going to 16.3, the next the other chapter, and we're going to kind of work out. We're going to work out this example. Okay, we're going to work out this example. Then we'll talk more about the definitions and so forth. Because like when you simulate, it's just easier to understand. You get a more feel for it. Okay, so let's see what this says. Black Sheep Scarves will open several new production facilities, and each facility has inspector. So you got the scarf, scarf that you put around your neck when it's cold, so they make these scarves, and before the scarves go out, before the scarves are shipped, each has to be inspected by an inspector. So each facility has one inspector who checks the wool scarves before they are shipped. Okay, now the problem is that sometimes maybe one inspector is not enough. It's kind of like your scarves are your customers. You got the scarves that are kind of waiting in line to be inspected, and you have a server who is inspecting the scarves. So you got scarves are the customers, you got inspector who is your server. We're thinking maybe one server is not enough because you have like many scarves that need to be inspected. So that's the question. So what is it we want to do? We want to make sure that we don't want the scarves to wait too long. Now, why would you worry about the scarves waiting? Do they complain? Will the scarves say, oh, I've been waiting too long in this line. I gotta go and I want to go ahead and home and have dinner, and you are keeping me here in this line. Now, why do we even care about how long the scarves wait?
You want to minimize the percent and ship it to the customer.
Right, you want to ship them. You want to get them out the door. You don't want them just sitting around, like not making you money. You gotta, get them out the door and make money and collect your payment. So you don't have like too much inventory of scarves that are just kind of just sitting around and waiting. So even though scarves are not humans and they don't complain, we still have to make sure they don't wait too long. So we want to make sure that the average waiting time is under 1 minute. Average waiting time for the scarves is under 1 minute. Okay, so what we're going to do is we are going to go over to first to get a feel for this. We're going to look at like 10 customers or 10 scarf situation. So we'll have 10 rows of simulation. And here we are told the distributions, the interarrival times. That's the time between two successive arrivals. So scarves are arriving. So scarves are arriving to your line. So what is the time between the arrivals, between the first scarf and the second scarf? And what is the time between the second scarf and the third scarf? So what's the time between the arrivals? And we are told that these times have uniform distribution. And we're also told that the service time, how long it takes to inspect one scarf, has a normal distribution with a mean of 2 minutes and standard deviation of 0.5 minutes. So you have here two random variables, the interarrival times and the service times. And then given this, we're going to generate the interarrival time and the service time for each scarf and then calculate how long each scarf has to wait. And we're going to do it, first we're going to do it manually, and then we're going to do it in Excel, with formulas. So first here is 10 scarf manual simulation. Okay, and you guys know how to generate numbers from uniform and normal distribution, so we're not going to go through it right now. And so that's already given, here's a formula for uniform distribution, and here is a formula for normal distribution. So we have already generated the values for our inputs, and what we're going to do is we're going to make a kind of like a Gantt chart for our customers. So you could think of customers as the tasks to be done, activities to be done, like in the projects and the scheduling. So for each customer, you have a bar. You have a bar on the timeline, and then we're going to calculate all these numbers. When do they arrive? When do they start the service? And how long do they wait? And when do they leave? What's the completion time? And what is the total time in the system? Time in the system means the queuing time, waiting time, plus the service time. Waiting time plus the service time. Okay, so we're going to do that, do these calculations, and let's make a picture here of our customers. So here we are going to have, let's make sure I got I want blue. Okay, so here's customer 1. Okay, let's see, that is my scarf number 1, the scarf number 1. Okay, and it says interarrival time is 1.4 minutes, so this means starting from time 0. So time 0, 1.4 minutes into the simulation, you have the first scarf arriving to your system. So let's see, time is, here is a time is 0 here, now here is, let's say, 1.4, and okay, so this person, scarf number 1 arrives at time 1.4. Okay, now we gotta think about, let's see. So arrival time is, the same thing, 1.4, and the service start time. Now, when you start the simulation, there is no other scarf. So assuming that no customer, so no customer at time 0. At time 0, no customer. Then this scarf is alone, and there's no other scarf, so this scarf doesn't have to wait. So service start time is the same as the arrival time, so it's like just equal to each other. So as soon as the scarf arrives, it will be inspected. It will be inspected. Okay, so no waiting time here. And then it says service takes 2.3 minutes. 2.3 minutes, so let's see. 2.3 is 2.3, so you start at 1.4 and then add 2.3, so that gives us 3.7, right? So that gives us 3.7. now this scarf could leave at time 3.7. So completion time is 3.7. 3.7. And what is the time in the system? Well, it's the same as 2.3. Like the same as service time because didn't have to wait. So time in the system is just 2.3. Okay, so it's pretty easy, right? And let's see, maybe we do like first 5. So we do the second one. Second customer or second scarf comes at time 1.3 minutes after the first one. So 1.3 minutes after the first one. So it's 1.3 plus 1.3 plus 1.4 gives us 2.7. Okay, so 2.7 minutes into simulation, the second one comes. So it's about somewhere over here. Okay, so over here, 2.7. And then we gotta ask, let's see, does the second scarf have to wait?
Yeah.
Oh, right, because when the second one comes in, there's the first one is still being served. The first one is still being inspected. So it has to wait until when?
3.7.
Until, right, 3.7. So wait here, and then at time 3.7, then the second one will start service. So here the time of starting service is 3.7. So gotta wait till the first one leaves. So this came from here. Came from here. 3.7 came from here. Okay. Now what is how long does the scarf have to wait?
1.
Yeah, so 1 minute. So 1 minute has to wait. And then starting service at time 3.7. Now how long does it take? 1.5 minutes. So 1.5 minutes, that's 3.7 plus 1.5 is 5.2, right, 5.2. So 5.2, that scarf could now leave, So time in the system is, well, there is 1 minute plus 1.5. So waiting time is 1 minute and service time is 1.5. So it's 2.5 minutes was the time in the system. Okay, and let's go to number 3. Number 3 is arrives at 4.9 minutes. That's a kind of long time after the second one. So that would be 2.7 plus 4.9 is 7.6. So at time 7.6, the third one comes. So it's way over here. 7.6 comes and nobody there. Okay, nobody there competing for the inspector. So start service right away. So same time 7.6, no waiting time. And then the service is for 2.2 minutes. So 2.2 minutes is 9.8. 9.8 and then gone. Oops, it's right here. 9.8. Leaves at time 9.8, and time in the system is the same as the service time, so it's 2.2. Okay, now number 4. Number 4 comes 3.5 minutes after the number 3. 3.5 minutes after number 3, so it's, you gotta add 7.6 plus 3.5 is 11.1. So number 4 comes at time 11.1. So number 4 doesn't have to wait either. So I go here, 11.1, and no waiting time, and start service right away at time 11.1. Okay, and completion time is, well, did I add the 2.5? So 2.5 minutes receiving service, and it's 13.6 is when this one leaves, 13.6. And time in the system is the same as the service time. So because there was no waiting, 2.5. Okay, now number 5 comes, there's really a short time between the number 4 and number 5. Only 0.7 minute after the number 4. So it was like 11.1 plus 0.7 is 11.8, right? 11.8. So number 5 Oh, there's no space. Number 5, 11.8 is about here. So that over here is 11.8. Sorry, sloppy. Okay, so that's 11.8 right there. And so that one has to wait. Until when?
13.6.
Until, right, this one leaves. So 13.6. So has to wait, and so start service at 13.6, and the waiting time is a difference, which is 1.8. Is that right? Yeah, 1.8 minutes. Then we have service time is also 1.8. So let's see, 13.6 plus 1.8 is 15.4. Yeah, so 15.4 is the time of departure. Okay, and the total time is the whole thing here. So maybe I could just say 15.4 minus the 11.8. 11.8. So that's 0.63, 3.6. Or I could just add a 1.8 here plus the 1.8. Waiting time plus service time is 3.6. Okay, so you could see how we could fill in the entire table like this. Let's just use Excel now. Okay, so I'm gonna go over here. Let's see, what do I need? Okay.
Just
Okay, I just stupid mistake. Okay. Okay, so we've seen the pattern, so I think we could figure out what to do. But in case you're not sure what to do, here's a guideline. What to do here. And so interval time is time between the arrivals. And of course, arrival time is the previous customer's arrival plus the interval time and so forth. So I just go over here. Okay, so this one is just just this number here, right? And the service start is equal to, well, same as the arrival time. So first one doesn't have to wait. So all these times are the same for the first one, 1.4. Now waiting time is service start time minus the arrival time, right? So time between the arrival time and the start service, Now the completion time is, you could do it either way. You could go do waiting time plus the service time, or you could say, no, actually no, that's the only way. Okay, never mind. So waiting time, no, wait, what am I? So completion time is, okay.
service starting time also.
Right. Okay, is service start time plus the plus the service time, right? Okay. So when you start plus the and then service, right? Like we've been doing here. Service start plus the service time, and the time in the system is. This is what I meant when I said either way. I could add the waiting time plus the service time, or I could do completion time minus the arrival time. Okay, so let me write that down. So I could do, let's see, column number is 6 is the waiting time plus the service time is 8, or I could do, let's see, completion time minus the arrival time. So either way will give me the same result. So here I'm going to say completion time minus the arrival time. That's one of the choices. Okay, now the second one. Okay, now the second one is arrival time is, you gotta add, right? So the previous customer's arrival time plus our customer's inter-arrival time. So previous arrival time plus the current customer's inter-arrival time gives me the time that our current customer comes. It's 2.7. And start services, okay, this is where we gotta read what the little blurb here. So it says, service start time is going to be whichever is later between the your arrival time versus the completion time of the previous one. So if you come after the previous one leaves, then you get to get the service right away. Now, if you come before the previous customer leaves, and you gotta wait for the previous customer to leave. So it's whichever is later, either your arrival time or your predecessor's departure time or completion time, whichever occurs later. So that's what it is here. So here I just have to go over here and then say later, whichever is later, my arrival time versus number one's completion time. So when my predecessor leaves versus when I arrive, whichever is later. Okay, so that's the biggest thing you need to know about the this whole simulation table. Okay, and then so this part is different for between the first and the second customer. Everything else is the same. Everything is so I should kind of say here. Here's a note. Okay, this part is different for the first customer. Others are the same. Okay, so here I copy this one and drag it down for the other customers. And then the other stuff I could just copy from the first customer down. Okay, so I copy here, and here I copy down all the other. Oops, no, copy down to here. Okay, so I have done a simulation of 10 customers or 10 scarves. Okay. Any questions? Okay, so here so far what we have is we got the waiting times for, so we know like how long each customer waits and how long each customer spends in this system. So these are the kind of the outputs that we get from the simulation, and then we take the average to come up with a single value, a single average waiting time and the average time in the system and so forth. So we'll do further analysis next time. So for now, we are going to pack up. So today's Monday. So see you guys Wednesday.